Everyone, welcome back to EECS 281. Before we begin, does anyone have any questions? All right, if you do, please let me know before class ends, or I'll stay a little bit afterwards in case anyone has any questions. But let's jump right in. All right, we're going to start by talking about the Fibonacci sequence. We're going to start with an example and then build up to more use cases. But a Fibonacci sequence is defined as we're going to start with 0 and 1. And then the nth Fibonacci number is the sum of the last two. So the n minus first and n minus second Fibonacci numbers. So for this case, 13, it is 5 plus 8. And we build it up, I guess, from 0 and 1. So 0 and 1 together gives us 1, 1 and 1 together gives us 2, and so on. We can write this down in a recurrence relation. What a recurrence relation does is allow us to implicitly define the function with respect to other calls of the function. So we know when n equals 0, n equals 1. These are our base cases, 0 and 1. So we can just return that. And then every other index, n is our index, so this would be 0, 1, 2, and so on, is just the sum of the last two Fibonacci numbers. So for instance, the fourth is going to be 0, 1, 2, 3, 4. It's right here, and it's the sum of 1 plus 2. All right. So in code, this is what this looks like. We have if n equals 0, 1, our base cases, return that number, else return the sum of the previous two fib numbers. The problem with this is that we will make a lot of recursive calls over and over again. So this will overload the call stack. Let's see what that looks like. So say we want to calculate the sixth Fibonacci number. What we're going to do is we're going to split it up into 5 plus, or the fifth plus the fourth. And then each one of those we have to split up into their respective breakdowns, 4 plus 3, 3 and 2. And then each one of those also has 2 together. So we're going to break down really quickly. We have a lot of calls made on the call stack. So in order to calculate just the sixth Fibonacci number, we want to calculate that once, right? In order to do so, we have to calculate the fifth one once. In order to do that, we have to calculate fib 4 and so on. So we'll calculate the fourth Fibonacci's number twice, the third 3 times, all these blue nodes, and so on. As you can see, we have a lot of calls, Fibonacci calls onto the call stack, but we're really only doing 6 different operations. So it doesn't make sense to do so many calls. This algorithm is O of 2 to the n because O of 2 to the n nodes is a factor times 2 to the n. So how can we improve this? Well, we're going to use dynamic programming. The idea is that whenever we compute a Fibonacci number, we store it in a vector that we can access for later. So we won't have to call fib 4 and break it down into 3 and 2 if we already calculate it here. So what this looks like is we start with fib 6, breaks down into fib 5 plus fib 4. And then because we start with the leftmost node, we're going to continue breaking this down. Is fib 5 in our vector? Nope. So we're going to break it down into 4 and 3. And then continue down to fib 2. It's not in our vector, so 1 and 0. 1 is our base case. That's 1. 0 is another base case. That's 0. So then now we're at fib 2. We just calculated 1 and 0. So now we can say, okay, it's 1 plus 0. That's 1. Now we're at fib 3. Fib 3, we had to go into calculate, so that's 2. We just found that, plus the fib 1, so that is 2. Likewise, we're going to look at fib 4. This is where things start to get interesting. So fib 4, we just calculated fib 3, so then we would add fib 2. Fib 2, we will check in our vector to see if it's in our matrix. It is, so then we just add the 2 together. In a similar way, we're at fib 3. Is fib 3 in our matrix? It is. So now we add it to the fib 4, which we just found, and that's 5. And final one, we check, okay, is fib 4 in our matrix? It is. So we can just look it up in the matrix, add these 2 together, and return 8. So this is what the code looks like. It's called the top-down approach because we start at the top. We start at the value that we want to end up with, the top, and then we make recursive calls downward, but we only calculate what we need. We store everything in what is called a memo. That is what this matrix is called. Finally, we have a different approach that what if we started from the bottom and built our way up? So we'd start off at the base cases and build up. That is called bottom up because we do start at the base cases and then we continue on until we get to 6. So what that would look like is we'd have 0, 1, add 0 and 1 together. We get 1, add 1 and 1, 2, 1 and 2 is 3, and so on. So that is what this code looks like here. That is what we just did. All right. Thanks for stopping by and have a great day.